are 0002 1001, a normal binary representation of BCD values. Now we know that how to convert a binary number into the BCD format. Already we have seen in last lecture. Okay. Now, as my K-map is handling only up to the 4 variables, I am going to consider 0 to 9 BCD values as the valid BCD values. After 9, 10 onwards, when I want to represent the BCD values in binary representation, at that time I need to use the 5 bits B0 to B4. And by using 5 variables in a K-map, it is not possible to simplify the expression. That's why I am considering 0 to 9 as a valid BCD bits or a digits. Now by applying XS3 code conversion technique, all the BCD values 0 to 9 are converted into the XS3 code. Now let's take the example again. I have a value 5 BCD in a binary representation. It is represented as 0101. It is a BCD 5. Now when I want to convert this into the XS3 code, then I have to add 3 into the number. Now after adding 3 into the number, the answer will be 110 carry will 1, 110 carry will 1, 110 carry will 1 and 1. Now the XS3 code for the 5 is 1000. Now here in the table you can see for a 5 decimal the BCD value is 0101 and the XS3 code is a 1000. Similarly, when 3 is added to the 0, I will get the answer as a 3. When 3 will be added to the 1, I will get the answer as a 4. When 3 is added to the 2, I will get the answer as a 5. When 3 will be added to the 3, answer will be get as a 6 and so on. Now by applying the conversion technique, this is the truth table for the BCD to XS3 code conversion. This is a truth table of BCD to XS3 code conversion. Now once we get the truth table, now we want to simplify the truth table by using a K-map technique. Now we need to draw the K-maps or for all the Now here the XS3 codes E0, E1, E2 and E3. These are the outputs. My input is B0, B1, B2 and B3 and after applying a XS3 code conversion technique, my output is E0, E1, E2 and E3. So for each output variable, I need to construct the K-map. There are 4 outputs E0, E1, E2 and E3. So I have to draw the 4 K-maps. Now to draw the 4 K-maps, now I have used a 4x4 variable K-map. Okay. Now I am drawing 4x4 K-map. This is the first K-map for a E0. Now for E0, the variable names I have to represent as B3, B2. Then B1 and B0. After plotting E0 output onto the K-map, now my K-map look like this: 1, 0, 0, 1, 1, 0, 0, 1. Then 1, 0. These are 0, 0, 0, 1, 1, 0 and 1, 1. 0, 0, 0, 1, 1, 0 and 1, 1. Now this is the cell number 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now after 9, 10 onwards, all the cells are the don't care cells. As in my BCD table, I have considered till 0 to 9 valid BCD numbers. So 10 onwards, all the numbers are the don't cares. So I am going to represent all these values as a don't cares. Now after plotting all the cells of a K-map, now we'll try for a grouping. Now here I can make a octet. These four cells and these four cells I can group together and I can make a octet. Now the expression for this octet, horizontally all the cells, that is a B2, B3, B3, B2 bar, then B3 bar, B2, then B3, B2, B3, B2 bar, all cells will lost. Now vertically the common variables, that is a 0. 0 is nothing but B0 bar. So the expression for E0 is B0 bar. This is the expression for E0. Now we'll draw the K map for the E1. 4 by 4 variable K map. The variable names I am using here as B3, B2 and B1, B0. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0 and 1, 1. This is a K map for E1. Now after plotting the output cells of the truth table in a K map, my K map will look like this: 1, 0, 1, 0, then 1, 0, 1, 0 and 1, 0 till 9. Then after all the cells I am going to represent don't care cells. Now first we'll try for the octet. Is the octet possible here? No. Then we'll try for the chord. Yes, chord is possible here. This is my first chord and this will be my second chord. This is a group number 1 and this is the group number 2. Now after finding the terms representing by the group number 1, horizontally all the cells will lost, vertically 0, 0, that is B1 bar and B0 bar, group number 1, plus group number 2 is representing horizontally all the cells terms will lost, vertically the variables are B1, B0. Now again we know that A bar, B bar plus AB is nothing but XNOR operation. Now I can represent this expression as B1 XNOR B0. This is the expression for the E1. Now we'll draw the K map for a E2. Now again 4 by 4 variable K map I am going to draw. And this is E3. B3, B2, B1, B0, B3, B2, B1, B0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. This is the E2 and this K map is for E3. Now after plotting the E2 row, E2 column of the truth table onto the K map, now the K map for a E2 looks like this: 0, 1, 1, 1, 1, 0, 0, 0, then 0, 1, and remaining cells are don't cares. Now we'll try for the octet. Octet is not possible. Then we'll try for the chord. We can make a chord of this group and this group. Then this is my group number 1. Now we can make a chord of this and these two cells. This is group number 2. And we can make a pair of this, that is a group number 3. Now we'll find out the expression. Now group number 1. What the group number 1 is representing? Horizontally the common variables are B2 bar. Vertically the common variable is B1 plus group number 2. This is again B2 bar and vertically it is representing B0 plus the pair it is group number 3. Pair is representing the common variable B2 and vertically B1 bar and B0 bar. Now from these two, I can take a common B2 bar outside and internally it is B1 plus B0 plus B2, B1 bar and B0 bar. Now this is the expression for E2. The K-map for a E3. Now after plotting the cells on a K-map for a E3, E3 will look like this: 0, 0, 0, 0, 0, 1, 1, 1, then 1, 1, all are don't cares. Now we'll try to make a octet. We can make this as a octet. This will be my first octet. Now we can make, this is a group number 1. Now we can make this as a chord. This will be my group 2. And we can make this one as in one more chord, which will be my group number 3. Now we'll find out the expressions. Group number 1 for octet, vertically all the variables we lost. Horizontally the common variable is B3 plus group number 2. Horizontally the common variable is B2 and vertically the common variable is B1 plus the group number 3. Group number 3 is horizontally it is B2 and vertically it is B0. Now again, after taking the common variable B2, I can rewrite the expression like this: B1 plus B0. Now this is the expression for E3. E3 is equal to B3 plus B2 and internally B1 plus B0. This is the expression for E3. Now after finding all the expressions for E0, E1, E2 and E3. Now my next task is design the logic circuit for all these output variables E0, E1, E2 and E3, which is nothing but the XS3 code converted for the given BCD numbers. Now I will try to design the circuit. Now I will take the common variables B0, B1, B2 and B3 and their inverters, and then we'll give the inputs to implement these expressions. Now let's take the common inputs. The common inputs are, I am taking here as B0, B1, B2 and B3. I need the inverter values, so I am giving the input to the NOT gates, which will give me the bar values. B1 given as input to the NOT gate, which will give me the B1 bar. B3 I will give the input to the NOT gate, will give me the B3 bar. Now first we'll implement the E0. Now E0 is equal to D0 bar. So E0 is equal to B0 bar. So B0 bar. This is B0 bar, which is nothing but the output E0. E1 is equal to B1 XNOR B0. Now B1 will take, this is a B1. Now XNOR gate, I am going to use here the XNOR gate, the input. Now the output is nothing but E1. The input is B1. First input is B1. Second input is B0. And it is giving me the E1 as a output. Now we'll implement the E2. Now for E2, we need two AND gates. Now for first AND gate, given as D2, it is a B2, first input, second input B1 bar and B0 bar. B1 bar and B0 bar. B0 bar and B1 bar. And output I am getting as B2, B1 bar and B0 bar. This as a first input to my XOR gate, which is giving me the output as a E2. Now the second input we will derive. For the second input, the first OR gate will perform the addition of B0 and B1. First OR gate will perform the addition of 0 and B0 is my first input. Second input is B1. This will give me the output as B0 plus B1. This will give as an input to the AND gate. My AND gate will take the first input and second input is D2 bar, B2 bar. So this second input I am giving as a, this is a B2 bar. It is giving me the second term and that I am giving as a second output to the OR gate, which is nothing but B2 bar and B0 plus B1. And the first term is B1 bar, B0. Now we implement the E3. Now for E3, again I need to take the OR gate, AND gate and one more OR gate. Now for E3, the first input is D3. To the OR gate, I have to give the input. First we'll find out the D2 and D0 D1. Now OR gate I am using here to get the D0 D1, B0 B1. Now the B0, this is the B0 and this is B1. This is B0 plus B1. Now this will be the first input to the AND gate. Second input is B2. Now this is the B2. I am giving as a second input, which is a B2. And it is B2 into B0 plus B1. This is the first input to the OR gate and second input is the B3. Now this is the B3. B3 as a second input to the OR gate, which is giving me the E3. This is the logic circuit of BCD to XS3 code converter. This is the logic diagram. I hope all you have cleared the concept how to design BCD to XS3 code conversion and how to implement that by using the different gates.